up to this point, we've learned how to measure things. We've learned the alphabet, which is symbols for our elements. We learned how to make words, which are the compounds. Now we want to take those compounds or individual elements, as the case may be, and put them together in a reaction. So we need a standard way to express that. And the chemical reaction equation is laid out with reactants on the left-hand side and products on the right-hand side. Get that out of the way. With an arrow in between. And for now, we're only going to put the arrow in there from left to right. But later on, you'll find out that these reactions can run backwards. When we get to a discussion of equilibrium, then we got to run them backwards too. And this happens at the same time as the forward and backwards. But for now, we're just going to have an arrow to the right. Okay. So in this case, this equation is balanced. What we mean by that is all of the atoms on the left-hand side show up on the right-hand side. So if you count the number of atoms, say 2 carbons, then you need 2 carbons over here. And this is called a coefficient. It's a multiplier. And when you see it in front of a compound or in front of a bimolecular element, for instance, in front of an H2, it means that there are 2 of those, whatever follows. So here we're saying there are 2 CO2s. That means we have 4 oxygens and 2 carbons on the right-hand side. So here are 2 carbons, there are 2 carbons. Here we have 6, 7 oxygens, okay, going into the reaction. On the product side, we have 4 oxygens and 3 oxygens make 7, so it's balanced. And this balancing procedure explains why Lavoisier's law of conservation of mass works. Because we didn't create anything, we didn't destroy anything in the process. Everything that was on the left shows up on the right. Hydrogen, we left hydrogen. So there's 5 plus 1 is 6. 6 hydrogens, and 2 times 3 is 6 hydrogens. Okay, so this equation is balanced. What we want to do is learn how to take an unbalanced equation and balance it. All right, one thing, this is, I guess you'd call it a caveat. When we write the balanced equation, we're assuming, for argument's sake, that everything on the left ends up on the right. The conversion is 100%. We're going to find out later that that's not true, but we got to start somewhere, and we're going to start with the easiest approach. And besides that, when we say that, we're reacting A and B and we're making C and D, this is an overall reaction. In other words, this is what we see going in and what we see coming out. But in here, there's usually a lot of activity, stuff that you don't see. And we'll tackle that later. Okay, so once you've got your elements and compounds written correctly, so that's extremely important that you learn how to write compounds. Once they're written correctly and put in the reactant or the product side, and most of the time, you'll just be told what the products are. You don't have to figure it out. There are a couple of cases where it's logical and you will be expected to generate products based on the reactants. But those are limited cases, and I'll forewarn you when we get there. Once you get these compounds and elements written correctly in the reactant side and the product side, then those formulas are chiseled in stone. You cannot touch those formulas. The only way you can balance the equation is with coefficients. You can put numbers in front of each one saying, I need 2 of these, I need 3 of these, whatever. But once you've written the compounds correctly, you can't touch them anymore. And by the way, if you don't write them correctly, then your equation will never balance. So that's a clue. If you're sitting there and you're going through time after time after time and you just won't balance, go back and check your formulas to be sure they're written correctly. All right. This is just up there for posterity. The best way to understand how to balance an equation is just do it. So you can read all that stuff you want. Start with an unbalanced equation. You've got reactants, products, so forth. I will point out that most textbooks say, after you get this far with your unbalanced equation, they say balance the equation by inspection, which is a cop-out. I mean, you can't tell students to balance by inspection and then don't give them any guidance, right? That's because whoever wrote the textbook is lazy. Now, not all of them are. There are some textbooks that go into detail, and most instructors will help their students learn tricks and tools to balance equations. But the more you do them, the easier it gets. All right. These are helpful hints, and there should be, did I hand out a copy of helpful hints? I think I did. Yeah, there's a copy of helpful hints that I handed out in class. Looks like this, and it's going to be up here. I hope it's the same. We shall see. Now, these helpful hints are not going to mean anything until you start to balance equations. So let's just leave them there for reference. Okay. Here's an example. This is probably not the best place to start, though, because it's got polyatomic ions. That can be confusing. We need to start really simple. How about we put the first one that I ever showed you up here? We're standing up looking into the engine of the space shuttle, and they're getting ready to light it. You don't want to be there when it turns on, of course. But the reaction that occurs is they're mixing hydrogen and oxygen, and they're making water. Okay? Now, you can tell right off the bat, we've got the right number of hydrogens, but we don't have the right number of oxygens. So in order to get 2 oxygens on this side, you need 2 there. But now you've messed up the hydrogens. So now you need 2 here to make 4 hydrogens, 2 oxygens. That's balanced, and that's a really easy one. Let's see. I'm going to go to the next slide, actually. See if we've got some easier examples. Okay. All right, I'm going to show you a method for balancing equations. I call it our budget. And it has 2 advantages. It keeps you from wandering off when you're trying to put coefficients in there and trying to remember what's what. And it instantly tells you when you have a balanced equation. So let's say we have calcium oxide. Let's see, let's put it right about here. And then carbon, and notice I leave a space there for coefficients. And then we have calcium carbide and carbon dioxide. Okay, so my budget method takes each of the elements that's in the entire equation and runs them down the side here. So we have calcium, and oxygen, and carbon. Calcium, oxygen, carbon. Okay, everybody's accounted for. Now you do an inventory. What's on this side? We have one calcium, one oxygen, and one carbon. That's your starting point. On this side, we have one calcium, we have two oxygens, and we have 3 carbons. Okay, so you can see right off that this is not balanced. Calcium's okay, oxygen's not, carbon's not. So the question is, where do you start? Well, one of those hints was if you have an element, a single letter element, you can have big letter or small letter, but it's not a polyatomic. I mean, it's not a diatomic, triatomic, so forth. Actually, it works with that too. If you have an element by itself, then save that to last. Because when you start putting coefficients in here, in front of these compounds, you may only want calcium's balance, but you're going to affect carbon too. But if you save it to last, when you put a coefficient in front of that, that's the only one that's affected. So save that to last. Okay, so we're not going to do carbon yet. So let's look at oxygen. We've got 2 oxygens over there. We need 2 over here, correct? So there's 2. Now you do a re-inventory. Right, now we have 2 calciums and we have 2 oxygens. Oxygen's balanced. We're still holding carbon to the end. Calcium, now we need 2 calciums over here. But we've made 4 carbons. Plus 1 is 5, correct? All right, so now we've got calcium, oxygen balanced. Now we can balance our carbons. We need 5 carbons over here. And you can see with this budget, you can see exactly 2, 2, 2, 2, 5, 5. You know it's balanced. Okay. And to answer this question, let's see, more than one correct? Well, what we try to do is have coefficients that are simplest whole number ratios. And these are ratios. You have 2 of these for every 5 of those, and you produce 2 of these and 1 of those. Okay, those are ratios. And you can't simplify them anymore because that's a prime number. But you could have 4, 10, 4, and 2, and it would balance. But by convention, we want the smallest whole number ratio, at least at this point. We'll run across examples in the future where we need fractionals in front. But those are special cases, and don't worry about that. All right, so that one's the one we came up with here. That one is technically correct. And that one's technically correct, but the best is that one. Okay, so let's go back. Go back to that slide with polyatomics. That's one of the tricks. Okay, I've got this animated. There we go. So we have ammonium phosphate. Okay. Type 1 compound, that's a fixed charge. Calcium chloride, it's a fixed charge, it's type 1 compound. Just balance the charges. Calcium phosphate, instead of ammonium, now we have calcium phosphate and ammonium chloride. And those are written correctly. You just check out the charges. Right? That last one, all halogens are -1. Ammonium is a +1. Polyatomic ion. That's balanced. phosphate is a -3 and calcium is a +2 because it's an alkaline earth. Right? So when you have one like that, remember what you do? Cross multiply. Okay, so we have these and we've inventoried them. Notice that if you have a polyatomic ion on one side of the equation and it does not change, it's a polyatomic, the same polyatomic on the other side, you can use that as a balancing group. That simplifies things a lot. You don't have to split it up into nitrogens and hydrogens. If you have an equation where the polyatomic is broken during the process, then you have to go to individual atoms. But as long as it doesn't change from side to side, phosphate, you can use those as your balancing groups. And that simplifies a whole lot. Okay, so how many ammoniums do we have on this side? We have 3. How many phosphates? 1 calcium, and 2 chlorides. And on the other side, we have 1 ammonium. We have 2 phosphates. That's that subscripted 2. Right there. We have 3 calciums right here. And we have 1 chloride. Okay, so you can see right off that's not balanced. So the first question that should be popping into your head is, where do you start? Well, with experience, with practice, you get a feel for where is the best place to start. But at this point, if you don't see, and we don't have any individual elements off by themselves, so you don't have to hold anything in reserve. You can either start at the top, say ammonia, or you can start anywhere else. Say we've got 3 calciums on that side, we'll put a 3 there maybe. Let's see what I've done in the animation. I'm going to start with calcium. So we get a 3 in front of the calcium, and what that does is it changes the budget to 3, and then now we're going to go to, we also changed chlorines. Right? So we got to go to the other side, and we need 6 chlorines, don't we? On this side, because we got, on that side, because we got 6 over here. So 6 there, and then put a 6 over there. Okay. And then we need to re-inventory it, of course. So now we've changed the ammonias to 6 ammonias and 6 chlorines. Okay, we're getting closer. So where do we go next? Well, we haven't messed with this one or that one yet. We probably want to go right here because we've got 6 over there and we want 3 here. So what coefficient would give you 6 ammoniums on this side? 2, right? So now we can re-inventory the ammonias. We have 6 ammonias there. And that gives us 2 phosphates. And so we want to change that one to 2 phosphates. And you can see right off 6, 6, 2, 2, 3, 3, 6, 6. We're balanced. Okay. The review document should give you a lot of practice. We got lots of different ones in there. Okay. So let's skip over this one. This is just a reminder. Don't mess with the subscripts. So the balanced equation tells us the ratio of the number of molecules on each side. So if you have 2 on this side and they have coefficients, then they're ratioed to the products on the other side. what we can say is, actually, I should have stayed where I was. Oops, sorry. We'll use this one. Okay, so if we've got 2 calcium oxide and 5 carbons, 2 calcium carbides, and a CO2. It's important when we start doing calculations to become comfortable with the idea that the ratio of this calcium oxide to that calcium carbide is 2 to 2 or 1 to 1. So if we know, say if we have 4, and this could be molecules or moles, either one. If we have 4 moles of calcium oxide, how many moles of calcium carbide will we produce? It's not a trick question. 4 moles, because it's 1 to 1, right? Start with 4, end with 4. And if we have 10 carbons, because we doubled this one, so we got to double that one, right? Ratios that work here and they work here. So if we have 10 here, how many of these will we produce? 4. Just like before, right? 4, 10, 4. And then we would produce 2 of those because there's a 1, understood 1 in front of it. Okay? Those ratios are important. And we're going to use those ratios to create conversion factors. And they'll look something like this. Say we have so many moles of calcium oxide, but we want to find out how much carbon dioxide it'll produce, right? This is the numerator, is where we want to go. This is where we've been, and we want to cancel. So if we have X moles here, then we know the calcium oxide here and 1 there. That's the ratio. Right? So this cancels and leaves us with moles of carbon dioxide. So it'd be X times a half, whatever that is. Okay? Just giving you a heads up. That's where we're heading. And that's why you got to have a balanced equation. If you don't have a balanced equation, you're stuck. Let's see. Yeah. And we'll tickle it. All right. What we're saying with that example I gave you was that is the ratio of moles to moles to moles. But we can use that information to find out if we go in with 100 grams of one product, how much will it produce in mass? But there's a procedure for that because these equations are not related by masses. They're related by moles. That was the problem that the chemists in Europe in 1865 were having. They didn't know about this balancing of equations and relating things by numbers of atoms and numbers of molecules. They were stuck with mass, and the mass will get you there. All right. So how do we convert? If we know the ratio of moles, how do we convert those moles to mass? Or how do we take, if we know mass, how do we get them into moles so that we can use our balanced equation? The answer, molar mass. So we learned last Tuesday how to calculate molar mass of a compound. You just add up the individual molar masses of all the atoms in the formula. Okay, so we're going to balance the equation. We're going to convert the masses of the reactants or the products, depending on our starting point. You can start with products and work backwards. Using molar masses, we'll convert those masses to moles. Then we can use our ratios to tell us how many moles of product or reactant, as the case may be. Then once you find out how many moles that you can get, or how many moles you start with. Suppose you want the answer in mass again. Well, once you've got the moles of the compound as the end product or the starting material, then you can reconvert that back into mass for that particular compound. Okay? So it's obviously a multi-step process. All right, the best way is just to, if you like flow diagrams. So let's use this example. P4 plus 5 oxygen yields 2 P2O5. That's a solid, that's a gas, that's a solid. For our purposes, it doesn't matter. So you're given 6.25 grams of phosphorus. That's what you start with. What mass of oxygen is required to consume all of that? Okay? So the rule is, if you've got mass, you're stuck, you can't go anywhere. You've got to be moles before you can move in a balanced equation. Well, first of all, is it balanced? P4, yep, there's 4. 10 oxygen, 5 times, yeah, okay, so we're already balanced. So what we want to know is this in mass. All right, so how do we convert that to moles? 6.25 grams of P4. Right? If you want moles, moles are going to be on top. That's where you're headed. Grams is where you come from. Grams cancel. So we need a molar mass for P4. Let's see. 30.97 times 4. 28, 2 and 36 is 38. 3, 12. 123.88. And you can keep all of those significant figures because we're not going to have any add subtract in this calculation. You can keep all of them for now. So this is grams per mole of P4. So where does it go? Per mole. Remember, this is a conversion factor, which means it's equal to 1. And you can flip it. If it's equal to 1, it's okay. I mean, you just rotate it, it's still equal to 1. 123.88. Right? So we divide this number into that number, and we get the number of moles of P4. Okay? Let's see, have I already done this? No, I didn't. So I need to do this. Okay, so 6.25 grams and divide it by 123.88. So I get 5.045 times 10 to the minus 2 moles of P4. All right. Now that we got moles, we can go anywhere in that equation we want. But the question is, how much oxygen is required? So we need to find out how many moles of oxygen will be required to consume all that P4. Right? So we set it up like this. If I had more room, I could just work it on out that way. So this is moles of P4. We want moles of oxygen. Ratio to moles of P4. Right? The magic numbers here are the coefficients. Right? P4 is 1. Don't forget that. Just because we don't write the 1 doesn't mean it's not there. And then this one is 5. So 5 times that value would be how many moles of oxygen are required. And I get 2.552 times 10 to the minus 1 moles of oxygen. Right? We cancel this, left us with moles of oxygen. Now, since we're asked to do it in grams, we've got to reconvert. Right? So we need a multiplier here that will get rid of moles of oxygen and leave us with grams. Anytime you see grams and moles as a quotient, think molar mass. So what's the molar mass of O2? What's the molar mass of O? 16. Yeah, you were about to say it, weren't you? I was trying to read your lips. So 2 of them would be 32. 32 grams per mole of O2. So we just need to multiply 32 times that. Now we get 8.07, and I'm going to round it off. Since we started with 3 significant figures, I'm rounding it off to 2 grams of O2. That's our answer. Okay? That's how you do it. We use that same procedure to go this way, to go that way, to go here, to go there, or to go back here, anywhere you want to. Your starting point could be here. It might say, if I want 100 grams of P2O5, how many grams of P4 do I need to burn to get there? And you just work it backwards and use your coefficients to give you this ratio. You find out what do I need in here, and then you look for the coefficients in your equation.
Dr. Bly. I have a quick question. So where did you get the 2.552 from?
5 times this number.
Okay, so you did that.
Yep. I was going to put a
Okay.
equal on there.
Okay, thank you.
Okay. That gives us moles of oxygen, then I converted moles of oxygen to grams of oxygen. And that answers our question. Think of it this way. You got walls there. Nothing gets over those walls except moles. If you're not a mole, you can't go. All right. Let's see. What do I have? About out of time, huh? Do it. Oh, 1:45. Okay. I was about to panic. Notice that's coming cleaner today. I came in thoroughly clean forward and then I put some WD-40 on. Okay. Methane reacts with oxygen and air to produce carbon dioxide and water. How do we write that? Well, since we haven't talked about organic compounds, we're giving you the formula right here for methane. So we have CH4 reacts with oxygen. Is that the way it goes? Oxygen in the air. Remember, it's one of those diatomics. Right? If you miss that little detail, the rest of the problem is lost. And produces what? Carbon dioxide and water. Okay. So we can go through our budget and balance this. You want to do that? Balance it, do our budget. Okay, so we got carbon, hydrogen, and oxygen. That's it. 1 carbon, 4 hydrogens, 2 oxygens. Over here, we got 1 carbon, 2 hydrogens, and 3 oxygens. Okay. We're going to hold this one till last, right? Because it's an element. So let's look. Okay, carbon's okay. Maybe we'll do hydrogens first. 4 hydrogens here. We need 4 hydrogens there. That changes the oxygens. 2 plus 2 is 4. Now we need 4 of these. So I put a 2 there. I got 4 oxygens. Now we're balanced. Now we're going to compare that one with ammonia reacts with oxygen. Ammonia reacts with oxygen to produce what? Nitrogen monoxide and water. Okay? So we can do our budget for this one too. Nitrogen, hydrogen, oxygen. 1 nitrogen, 4 hydrogens, 2 oxygens. Here we go. 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. We need 4 hydrogens over here. So that gives 2 plus 1 is 3 oxygens. Correct? Is that right? We can do a recount. 1, 4, 2. Yep. 1 hydrogen, 4 hydrogens, 3 oxygens. Yep. Okay. Now, here comes the rub, and this is another trick. We need 3 oxygens over here. How do you get 3 out of 2? Right? That's evens odds. Here's the trick. Use a fraction. First use a fraction, then we'll get rid of the fraction after we're balanced. Okay. So if we say we need 3, what if we say 3 halves? 3 halves of that oxygen means that half an oxygen is only 1, right? But we need 3 of them. So we're good. Okay. Technically it's balanced, but if we want whole numbers, we have to multiply by some factor. Say multiply by 2. That gets rid of that fraction. And if you multiply the whole thing through by the same number, the ratios stay the same. They don't change. So here we'll have a 2. That 2 goes away. Now we got 3. We got a 2 here. And we got a 4 there. Okay. So we use that 2. 2 ammonias. Excuse me. You know what I did? I messed up. Nobody called me on it. All my students are that way. They like to watch me make mistakes. Let's try that again. NHO. Now we have 1 N, 3 H's, 2 O's. 1 N, 2 H's, and 2 O's. So now we need a different approach. We need to get the hydrogens to balance. All right, we've got 3 hydrogens on this side and 2 on that side. The hydrogen only occurs in that compound on the product side and on that compound on the reactant side. If that's the case, then you can use the cross multiplication trick. If we multiply this one times 3, right, and this one times 2 from there, now we get 2 nitrogens, 6 hydrogens, and over here we get 6 hydrogens, and we change the oxygens to 4. Okay, next, we need to balance the nitrogens. Okay. So that changes to 3 plus 2 is 5, right? Let's check ourselves again. 2 nitrogens, 6 hydrogens, 2 oxygens. 2 nitrogens, 6 hydrogens, and 2 plus 3 equals 5 oxygens. Now we can use the fraction trick because we need 5 oxygens on this side. There we go. Are we good?
So you don't need to multiply everything?
I'm sorry, say again?
So you don't need to multiply everything by a whole number?
Yeah, we do now.
Oh.
We got to get rid of that fraction.
Oh.
So if we multiply by 2, That makes this 4. That makes that 5. Makes this 4. And makes this 6.
So can we always multiply by 2?
Only if the denominator is 2. Right? You want to cancel that 2. And if you multiply 2 times any half fraction, you get rid of the denominator. If we saw an opportunity to put a 3 or 4 or 5 down here to get where we wanted to go, then you would use that denominator. Okay, so let me clean this up. That's 4. This is 5. That's 4. And this is 6. There we go. And looks like I'm kosher. All right. Now the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane? So these reactions are not happening together. We're just asking the question. If I have 1 gram of methane, how much water will it produce? And then we'll use that information to find out how much ammonia would produce the same amount of water. See where I'm going with this? So, let's see, do I need to do this one on the board? Oh, no, it's right there. Okay. So we got the balanced equations. Now we're going to take the first one and convert grams to moles of methane. Remember, if you don't have moles, you can't go over here. So we got that many moles of methane. We're going to convert that many moles of methane to moles of oxygen, water, excuse me, by putting this in the numerator and that in the denominator. So it's just 2 times. Good? Okay. That's how much water we need to produce over here, that many moles. So you put that many moles down here, and they'll work backwards to the ammonia. So we got this many moles of water here, and what's the ratio? Well, moles of water is what we want to cancel. So we put the 6 in the denominator and the 4 in the numerator. And that says that many moles of ammonia. Then we convert the moles of ammonia to mass by using the molar mass of ammonia. 14.01 plus 3.03. Right? 3 hydrogens, 3 times 1.01. 17.04. 1.42 grams of ammonia will produce exactly the same amount of water as 1 gram of methane in that reaction. Okay? Now, remember I said the way we have it set up, we're assuming 100% conversion. If we say this many grams of methane, then it's going to produce 0.1246 moles of water. But in reality, there's always some loss. Right? When you start weighing things out, when you start collecting products, you're going to lose some. So there's always, well, actually, I'm jumping ahead. That's efficiency. Limiting reactant refers to 2 or more reactants. If we have 1 gram here, and this is an excess, then we can ignore that. There's plenty. But if you're told exactly how much of each one, right, just say we have another gram in this one. Then you have to consider one of these is going to run out. Right? The one that the smallest amount by ratio is going to run out. And then that's when the reaction stops. So you might have, this would be, for argument's sake, say this one is limiting. That makes the other excess, which means there will be some of it left over. Okay? Now we need to figure out how to determine which one is limiting. Well, this is an artist rendition. If you were able to see the reaction on the molecular scale, this would be what's called a stoichiometric mixture. In other words, you have exactly the right amount of reactants so that there's none of them left and you produce only product. So see how they're paired up? Right? Got one nitrogen, three hydrogens, all the way down, all the way down, all the way down. And you get, for each of these, you get two ammoniums. Okay? That's what's called a stoichiometric mixture. That's theoretical. In real life, it never happens. Because when you start divvying out by volume or by mass, whatever the case may be, these reactants, experimental error is going to short one of them and excess the other one, usually. So this is our starting point. This is an idea where the limiting reactant in this case is hydrogen. Notice that hydrogen has paired up here, here, and here, but there's not enough of these guys. Their dance cards are empty. That means hydrogen is limiting. It runs out, and you've got nitrogen left over. And you will have nitrogen left over in the products. All right.
Dr. Bly?
Yes.
So in the question that we just worked through, where is the 16.05 from? In the question we just went through on the PowerPoint. The 16.05 grams.
I'm looking straight at it and not seeing it, right?
Is it
Oh, there it is.
the molar mass of the CH4?
Yes, that's the molar mass of methane.
Okay,
That's-
so
That's the way we convert mass to moles. We use this ratio. Right? Grams cancel, leaves you with moles.
okay.
Okay?
All right, thank you.
Okay. I better move ahead. Sorry. Or should I? No, I better stay here. Suppose with this balanced equation, which we did earlier, right? Hydrogen, oxygen makes water. You have 2 moles of hydrogen and 2 moles of oxygen. How many moles of product can you produce? Well, 2 moles of hydrogen only need 1 mole of oxygen, correct? So when this runs out, you still got a mole of oxygen left, but how many moles of water do you have? 2 moles of hydrogen makes 2 moles of water. Right? So you got 2 moles of water out of that reaction. What if we have 2 moles of hydrogen and 3 moles of oxygen? Sublime to ridiculous. Right? You got more oxygen and you still don't need. And these 2 moles make 2 moles of product. How about 2 moles of hydrogen and 1 mole of oxygen? That's the stoichiometric mixture. It's exactly the right ratio. 2 to 1 makes 2. So 2 waters, 2 waters, 2 waters, 3 moles of hydrogen and 1 mole of oxygen. Now the tables are flipped. 1 mole of oxygen will be completely consumed by 2 moles of hydrogen, and we'll have a mole of hydrogen left over. But that will still produce 1 to 2 moles of water. That's why the answer is they each produce exactly the same amount. Okay. So this is a cautionary note. You can't just simply add the total number of moles of the reactants to decide which reactant mixture makes the most product. You have to take them individually of the reactants and find out which one is the limiting one. And I got a procedure for you. How much product can be formed by using what you're given? So, as a general rule, the trick is take all of the amount of one reactant and say, what if all of it was converted to product? And you pick one of the products. Usually, you pick one that will answer the question. And then you take the other one and say, what if this one was used completely up and gave me that product? Right? Two different scenarios. Which one is limiting? The one that produces the least amount of product. And then you know which one is the limiting one. Okay. Oh, we're not going to do one. Okay. We got examples in here, and I thought I had the slide on there. Okay, maybe this last slide. Okay, I think we got time to do it. But the next slide, it takes off from where I digressed earlier. Percent yield. Can you expect 100% yield out of your reaction? No, you're always going to come up short. Every chemical engineer knows that. And what they try to do for their bosses is maximize the yield, right? Minimize all actually, the reaction that you got on the board, the balanced reaction, that's not the only one that's happening. If you're a chemical engineer, you know that there are side reactions, stealing product. But let's not go there right now. You can still lose product by spillage, by incomplete transfer, right? It's not a quantitative transfer of materials. Or if your product is a gas, you could have a leak. Right? Your gas goes. So we need a way to quantify our yield. And it's really simple. You know how much product you have gathered from the reaction. And you can also calculate how much product you expected to get because you know how much of the reactants went in. If you know how much reactants, you can calculate 100%. That's what this is. And then you get an actual number for the yield. And you just ratio the two and get a percent value. Most of the time, it would be less than 1 of 100%. If it's greater than 100%, that's probably a worse problem than losing some. Because you got something in there that's not your product. Okay, so here's our example. We're going to make PF3 out of a reaction with P4 and F2. Fluorine and phosphorus are going to react together, and it's probably a pretty energetic reaction. So here's our, and they've been kind enough to balance the equation for us already. So we have P4 and 6 F2 yield 4 PF3. Okay. What mass of P4 is needed? So many grams of P4 is needed to produce 85 grams of PF3. So we want 85 grams guaranteed. But we're also given percent yield problem. That's what we want to end up with as recovered material. But we know that there's some loss because the reaction yield is only 64.9%. So this number is going to be much, much greater than that. So what's the ratio? This is the actual. Right? We want to find the theoretical so we can work backwards to this value. Okay, everybody follow me? Sort of. So we know that 64.9% is equal to, let's say y grams. Can't use that because it's already taken. Divided, oh, excuse me. About to make a big boo-boo. Actual is 85 on top of PF3. And on the bottom is our y grams. Okay? So you can see right off that y is going to be bigger than 85. But this percent is incomplete. Right? Got to multiply by 100. All right. So how do we solve for y? The algebra says this in the denominator comes over here in the numerator, right? And this goes to the denominator. 85 divided by 64.9 times 100. So what did y come out to? Let's see. 85 divided by 64.9 times 100. I get 130. Let's keep a bunch of decimals here. 130.97 grams of PF3. That would be the 100% theoretical amount. Now we can use the equation because the equations are based upon 100% conversion. No losses. So we need to work backwards here. Okay, how do we do that? Can we go straight there now? No, we got mass, not moles. We got to make moles. So let's convert this to moles. 97 grams of PF3. Right? We need to get rid of the grams and leave us with moles. Okay, so we need to say, what is PF3 molar mass? Well, let's see. Phosphorus is 30.97, right? 30.97 grams per mole for that. And then 3 times fluorine, which is 19, rounded off 1900. 30.97 and 3 times 19, add those together. I get 87.97 grams per mole. So 87.97 goes in here. Divide that into 130. And I get 1.489. Moles of what? Moles of PF3. Okay? I can hear brain sizzling right now. Okay. So I'm going to have to erase some of this so I can make that conversion. So we have 1.489 moles of PF3, but we need to convert it to P4. So what's the magic numbers here? PF3 on the bottom, get rid of that one, and P4 on the top. So what's the ratio? Well, PF3 is 4, and P4 is 1. So we divide 4 into that number, correct? 0.372. 0.372. What is that? Moles of P4. Now we can convert that back to mass and answer the question. What do we need to convert that to mass? Right? What does that say to you? Molar mass. What's the molar mass of P4? Well, P is still 30.97, but we need 4 of them. And I get 123.88. Times that value, which is, my calculator says 46.1085. But we started with 3 significant figures, so we can only have 3. That's a 0. Let's go. 46.1 grams of P4 in this reaction will produce that much PF3 with, I raised it, with 64.9% efficiency yield. All right. Oh, I could have saved myself some effort. Well, there it is for you in black and white. Let's see if it comes up with the same value that I got. Yeah. 46.1 grams of P4. Okay. So between now and Tuesday, work on some of those problems.